Hello my friends, it's the NOLA MATHMAN coming again with another fun math adventure. Unlike Superman, I cannot leap tall buildings in a single bound, and I'm not faster than a speeding bullet. But in regards to math,
Superman got nothing on me.
After watching this video, students will be able to graph special functions while stating the domain and range. The concept we're looking at here is quadratic functions and equations. The skill we're looking at is special functions, how to graph and to determine the domain and range. So with no further ado, let's get into our lesson. So in this first example, we have this double like line thing. It says graph the function, state the domain. This is what we call a step function. That's the notification for a step function. So we will set up a table so we can get our step values. You'll understand how it looks when we start to graph. So we pick values of x. We create a column for that. We have a column for the x minus 2 because that's what you do in the step. That's the step equation. And then we put our little step, which is the nearest integer close to that value that you get. So you'll see what that means in a second when we do our table. So we pick values. We must include decimals here to kind of understand the step function. So we go from 2 to 4.5. 2 minus 2 is 0. The step for that, the integer closest to 0, obviously is 0. 2.5 minus 2 is 0.5. Again, the integer that's closest to 0.5 that is less, it can't be over, it's going to be 0 because it doesn't quite get to integer 1. It's not big enough. So it's between 0 and 1. So in the step function, we round it to the lowest integer. And so that's what you will see. 3 minus 2 is 1. When you get 1.5, that will go down to the lowest integer between 1 and 2, which is 1. And then we get 2.5, it'll be at 2. So how does that look when you graph? Well, you're about to see here. The NOLA MATHMAN is going to state how that looks. So you start at a value of x is 2, and it'll go on 0, meaning it does not, and the y is 0, so it stays on the x-axis. The next one is negative 1. That doesn't signify, these don't signify the ones that we have tables for. This is just the repetitive pattern of the step function. But the ones on top, as you can see, the one above the x-axis, that represents a step value of 1, and that's in the table there. And then you got the other one, which represents the step 2, which means any values between that 3 and 4 will be 1. And any values between 2 and 3 will be 0. And any values between 4 and 5 will be 2. And so that is a step function that we created. Now the domain for the step functions are all real numbers. There is no limitation on the values of x. So that's what we write. Range, which is the range of y values or the set of y values, are all real numbers because there's no limitations on what y could be. So our domain and range, and usually for all step functions, that's the same domain and range. So now we have an absolute value function here. F of x equals the absolute value of 2 times x. So again, we want to create a table and help us generate our points. Our first column is x, because we substitute x in and we solve for y. Since our y, f of x is simply y, so that is 2 times x, we put 2 times x. Then we do a third column that has the absolute value of whatever 2 times x is. And then our fourth column is the ordered pair that's 4. So you can pick any values of x that you want to do. Obviously, since we have a graph that are 5 units up, down, left, and right, we want to pick values less than 5, or values where 2 times x is less than 5. So we're going to go from negative 2 to 2. So when we plug in negative 2, 2 times negative 2 is negative 4. The absolute value of negative 4 is 4. Our first point will be negative 2, 4. So then we'll do that for each of the values. 2 times negative 1 is going to be negative 2. Absolute value of -2 will give us +2. And so our next value will be -1, 2, which will show up here in a second. Little NOLA Mathman is a little behind, and so we have our next value. So now we substitute 0 for x. 2 times 0, 0. Absolute value 0, 0. And so our next point is 0, 0. And we substitute 1 for x. 2 times 1 is 2. The absolute value of 2 is equal to 2. So the next point is 1, 2. And then when we substitute 2, 2 times 2 is 4. Absolute value of 4 is 4. And our next point is 2, 4. So when you graph these points, you would generate what we call an absolute value function. So what does a graph of absolute value function look like? So we're going to graph these points and see. So we have our first point, -2, 2 to the left, 4 up. And we go 1 to the left, 2 up. And we do 0, 0. And we go 1 to the right, 2 up. 2 to the right, 4 up. And we get a V-shaped curve. Not a parabola like a quadratic. This is the actual V-shaped curve. And we will draw that. And that is the form of how absolute values functions should graph. They graph in V-shaped graphs. So that lets us know that we've done it right. And now we have to write the domain and range. Domain, as you can see, x is going continuously to the left and right. So that means the domain is all real numbers. There is no limitation on the domain. The range, of course, is different because you don't see any y values below the x-axis. So you have to account for that when you give the range. So range is going to be all y values greater or equal to 1. And that's what we will write here for the domain. And so, I mean greater than 0, I'm sorry, because it starts at the x-axis. I said 1, it's y greater than or equal to 0. So that is our range. So we're done with that problem. So we've done a step function problem. We've done a absolute value function, and now we're doing another type of special function. Let's see what's next. So we're moving that stuff out the way there. And so now we're going to put up our next example. This looks different. It's 2 different f of x values, 2 different equations based on what the value of x is. We call this a piecewise function because it has 2 different pieces, 2 different functions. So what you do is you want to graph the first function, f of x equals x plus 2, when x is less than 0. So we're going to pick some values of x that's less than 0, and we're going to plug it in and get some points. So we'll pick -1, -3, and what other value? You can pick any values that's less than 0. NOLA Mathman just picks these values. So we substitute -1 plus 2, that's 1. Our first point is -1, 1. We substitute -3 plus 2, that's -1. Our next point is -3, -1. Then we substitute -5 for x. -5 plus 2 is -3. And our next point should be -5, -3. Now, since x is less than 0, at 0, we do not put a closed point. We will put an open point because 0 is not part of the solution. It's less than 0, so we put an open point at 0. Now, when you plug in 0 in there, you can see that 0 plus 2 is 2. So at 0, 2, you will put an open point for this particular graph. So we graph the other points that are given here. And we have -5, -3. We're waiting for that point. Get that. And now we must graph what y is when x is 0, but we will put a open point there. That will be basically at 0, 2. We put an open point. It's a linear function, so we connect the points from that open point, and that graph should show up in a second here. And there we go. And so that is the first part of our graph when x is less than 0. But we also have to graph f of x when x is greater than or equal to 0, which we will do next. So now we write that function. That function when x is greater than 0 is is 0.5x plus 1. So again, we want to pick values equal to 0 and greater. So we'll start with 0, and then we'll see what other values. You can pick any values greater than 0. So we'll see what the NOLA Mathman does. So we write a column for our x coordinate value. We get a column for our equation that gets us y, which is negative 0.5x plus 1. And then from there, we get our coordinate xy. So we'll start with 0. What other values? All right, we'll pick 1, and we'll pick, what else? 3 and 5. So we'll do 1, 3, and 5. Again, since the graph is 5 units up, down, left, and right, those are good values. So we're going to substitute into the equation, solve for y, and get our ordered pairs. And looks like the NOLA Mathman is expanding the second column because he needs room to do the work. That's why he's doing it. You want to do that on your own paper when you're doing these calculations. You want to have a nice wide column when you're doing your work like we're doing here. So when we substitute 0 for x, we get 0 plus 1, which is 1. The first point is 0, 1. So then we will plug in 1 here. Now it probably would have been better looking at the points. Since we have 0.5, it probably would have been better for the NOLA Mathman to pick 2 even numbers to get whole numbers, but it's good to do fractions. So negative 0.5 is negative 0.5 plus 1 is 0.5. So that's how you get that, and that will give us a 0.5. Then when you plug in 3, negative 0.5 times 3 is negative 1.5, plus 1, which is 0.5, negative 0.5. It'll be negative instead of positive. So your next point is 3, negative 0.5. Then when you substitute 5 into x, you will get negative 2.5 plus 1, which will give us negative 1.5. And that will be the value y, so you put 5, negative 1.5. So now we graph these points. Now since you have 0 can be equal to 1, instead of putting a closed point like we did in the first function, we will have a solid point for 0, 1, because it includes 0 as part of the solution. So now we graph 1.5, 1 to the right, 0.5 up, 3, negative 0.5, 3 to the right, negative or halfway down, 1. And then you say 5, that's 5, 1.5 would be 1.5 a unit. And so that creates a straight linear point, and so we connect those points. And now we have done our piecewise function. So a piecewise function is 2 functions that come together to make up one function depending on what the value is x. If it's one value at x, you use one equation. If it's another value, you use the other. And so this is an illustration of that. So we have now mastered the concept of solving special functions. The functions we have learned today are step functions, absolute value functions, and piecewise functions. So again, until we meet again for another math adventure, this is the NOLA Mathman signing off. Have a blessed and prosperous day.